How latching relays work. Advantages and applications of latching relays. Latching relays, also known as bistable relays, are a type of relay that maintains its state after being actuated without the need for continuous power. Unlike standard relays that require a constant power supply to keep the contacts in a particular position, latching relays only need a short pulse of power to change states. This feature makes them highly energy efficient and suitable for applications where power conservation is critical. How latching relays work. Latching relays typically have two coils, known as the set coil and the reset coil. Here's a basic overview of their operation. Latching relays, also known as bistable relays, maintain their state after being actuated without needing continuous power. Here's a more detailed look at their working principles and mechanisms. Basic working principle. Latching relays operate by using magnetic or mechanical means to stay in one of two stable states, set or reset, even after the actuating power is removed. They typically have two coils. Set coil. When energized, this coil switches the relay to the on or closed position. Reset coil. When energized, this coil switches the relay to the off or open position. Steps of operation. Initial state. The relay is in a default state, either set or reset, based on its initial design or the last actuation. Set coil activation. A pulse of current is applied to the set coil. This generates a magnetic field that moves the armature or other switching mechanism to change the contacts to the on or closed position. The relay stays in this position after the current is removed due to the latching mechanism. Maintains state. The relay remains in the set position without needing continuous power. Reset coil activation. A pulse of current is applied to the reset coil. This generates a magnetic field that moves the armature or switching mechanism back to the off or open position. The relay stays in this position after the current is removed. Mechanisms of latching. Latching relays can maintain their position through various mechanisms. Magnetic latching uses permanent magnets to hold the armature in place after it has been moved by the electromagnetic coil. When a pulse is sent to the set coil, the magnetic field from the coil and the permanent magnet holds the relay in the set position. A pulse to the reset coil generates a counteracting magnetic field to release the armature and move it to the reset position. Mechanical latching uses mechanical components like ratchets, cams, or springs to latch the relay in place. The mechanical mechanism ensures that once the relay is switched, it remains in that position until an opposite force from the reset coil is applied. Bipolar magnetic latching uses a bistable mechanism where the direction of the current in a single coil determines the state of the relay. A positive pulse sets the relay, and a negative pulse resets it, or vice versa. Circuit example. A simple latching relay circuit typically includes power source, provides the necessary voltage and current pulses. Control switches, used to manually apply pulses to the set and reset coils. Diodes, protect against back EMF generated by the relay coils when they are de-energized. Relay coils, set and reset coils to control the relay state. Load, the device or circuit being controlled by the relay. Example operation. Setting the relay. Pressing a switch connects the power source to the set coil, generating a magnetic field that moves the contacts to the closed position. The relay remains in this state after releasing the switch. Resetting the relay. Pressing another switch connects the power source to the reset coil, generating a magnetic field that moves the contacts back to the open position. The relay remains in this state after releasing the switch. Conclusion. Latching relays are versatile and energy-efficient components suitable for various applications requiring stable switching states with minimal power consumption. Their ability to maintain a set or reset state without continuous power makes them ideal for use in power-sensitive environments, ensuring reliability and efficiency. Latching relays offer several advantages over traditional relays, making them ideal for specific applications where efficiency, reliability, and stability are crucial. Here are some key advantages. 1. Energy efficiency. Reduced power consumption. Latching relays only require a short pulse of power to change states, set or reset, unlike traditional relays that need continuous power to maintain a state. This significantly reduces overall power consumption. Ideal for battery-powered devices. The minimal power requirement makes latching relays perfect for battery-operated devices, extending battery life. 2. Heat reduction. Lower heat generation. Since they do not require continuous power, latching relays generate less heat compared to traditional relays. This reduces the need for additional cooling and improves overall system reliability. 3. Improved reliability. Less wear and tear. The reduced need for constant energization means less mechanical and electrical wear on the relay components, enhancing the relay's lifespan and reliability. Stable operation. Latching relays maintain their position even during power failures, ensuring continuous operation without the risk of losing the set state. 4. Noise reduction. Quieter operation. The actuation of latching relays typically produces less noise compared to traditional relays, which can be beneficial in noise-sensitive applications. 5. Versatile applications. Variety of uses. Latching relays are suitable for a wide range of applications, including home automation, telecommunications, industrial controls, security systems, and energy management. Their ability to hold a state without power makes them particularly useful in critical systems where maintaining state is essential. 6. Compact design. Space saving. Many latching relays are designed to be compact, saving space in electronic designs. This is particularly advantageous in modern electronics, where space is often at a premium. 7. Cost efficiency. Operational cost savings. Reduced power consumption and longer lifespan lead to lower operational and maintenance costs over time, making latching relays a cost-effective choice. 8. Enhanced safety. Fail-safe operation. In safety-critical applications, the ability of latching relays to maintain their state without power ensures that systems remain in a safe condition even during power interruptions. 9. Environmental benefits. Lower environmental impact. Reduced energy consumption contributes to lower carbon footprints, supporting environmentally friendly and sustainable practices. Specific application advantages. Home automation. Latching relays are used to control lights, heating, and other appliances, maintaining their state without continuous power. Telecommunications. Useful for switching signal paths and circuits, ensuring stability and reliability in communication networks. Industrial controls. Ideal for managing motors, pumps, and other industrial machinery where reliable operation is critical. Security systems. Employed to activate and deactivate alarms and other security devices, ensuring they remain in the desired state during power outages. Energy management. Integrated into smart grids and energy-saving systems, latching relays help maintain efficiency and reliability. Conclusion. Latching relays offer a range of advantages that make them suitable for applications requiring low power consumption, high reliability, and stable operation. Their unique ability to maintain a set state without continuous power makes them an excellent choice for various modern electronic and industrial applications. Latching relays are versatile components used in various applications across different industries due to their unique ability to maintain their state without continuous power. Here are some key applications of latching relays. 1. Home automation. Lighting control. Latching relays are used to control lights, allowing them to be turned on or off with a momentary switch or remote control without requiring continuous power. Smart home systems. They are integral in smart home systems for controlling various appliances and systems, such as HVAC, curtains, and security systems, improving energy efficiency and convenience. 2. Telecommunications. Signal routing. In telecommunications equipment, latching relays switch signal paths and routes without needing constant power, ensuring stable and reliable connections. Network switching. Used in network switches and routers to maintain or change the state of network connections during power fluctuations or outages. 3. Industrial control systems. Motor control. Latching relays manage the operation of motors in industrial machinery, allowing for precise control and maintaining motor states during power interruptions. Process automation. Used in automation systems to control various processes, ensuring stable operations and reducing energy consumption in automated production lines. 4. Security systems. Alarm systems. Latching relays are used to activate and deactivate alarm systems, ensuring they remain in the desired state during power failures. Access control. Employed in access control systems to lock or unlock doors and gates, maintaining security without continuous power. 5. Energy management. Smart grids. In smart grid applications, latching relays help manage and distribute power efficiently, maintaining the state of various components during power fluctuations. Load shedding. Used in load shedding systems to disconnect non-essential loads during peak usage times, conserving energy and reducing demand on the grid. 6. Automotive applications. Power management. Latching relays are used in vehicles to control various electrical systems, such as lighting, infotainment, and safety systems, reducing the load on the battery. Safety systems. Employed in automotive safety systems, such as airbags and seatbelt pretensioners, to ensure they remain armed and ready without draining the battery. 7. Renewable energy systems. Solar power systems. In solar power installations, latching relays control the connection and disconnection of solar panels and batteries, ensuring efficient energy management. Wind turbines. Used in wind turbine control systems to manage the state of various components, optimizing performance and reliability. 8. Medical equipment. Life support systems. Latching relays are used in critical medical equipment to ensure they remain operational during power outages, providing reliability in life-saving applications. Diagnostic equipment. Employed in diagnostic machines to control and maintain the state of various components during procedures. 9. Consumer electronics. Power switches, used in consumer electronics like TVs, audio systems, and computers to control the main power state, reducing standby power consumption. Remote control systems. Integrated into remote control systems for various consumer devices, allowing for efficient power management and control. 10. Aerospace and defense. Aircraft systems. Latching relays are used in aircraft to manage critical systems, ensuring stability and reliability during flight without continuous power. Military equipment. Employed in military communication and control systems to maintain operational readiness and reliability in harsh environments. Conclusion. Latching relays are essential components in a wide range of applications due to their ability to maintain a set state without continuous power. This makes them ideal for energy-efficient designs, reliable operations in critical systems, and applications where power conservation is vital. Their versatility and reliability ensure they play a crucial role in modern electronic and industrial systems. Latching relays come in various types, each with specific mechanisms and applications. Here are the main types of latching relays. 1. Magnetic latching relays. Mechanism. Utilize permanent magnets and electromagnetic fields to maintain their position. Have two coils, a set coil and a reset coil. The magnetic field generated by these coils interacts with a permanent magnet to hold the relay in the desired state. Applications. Home automation, telecommunication systems, industrial controls. 2. Mechanically latching relays. Mechanism. Use mechanical components such as ratchets, cams, or springs to latch the relay in place. Once actuated, the mechanical mechanism physically locks the relay in the set or reset position until an opposite force is applied. Applications. Motor control and industrial systems.
Circuit breaker.
Manual override systems and automation. 3. Electrically held latching relays. Mechanism. Use an electric current to maintain the relay's position. Typically, a single coil is used, and the direction of the current determines the relay's state. This type requires a constant low-level current to hold the position. Applications. Signal routing and telecommunications. Low-power devices where minimal current is acceptable. 4. Polarized latching relays. Mechanism. Incorporate a permanent magnet and a polarized electromagnet. The direction of the current through the electromagnet determines the magnetic polarity and thus the relay state. Applications. High-speed switching circuits. Memory circuits in digital systems. 5. Reed latching relays. Mechanism. Use reed switches within a magnetic field to maintain their state. Activation and deactivation occur through magnetic pulses, and the relay state is held magnetically without continuous power. Applications. Precision instrumentation. Low-power applications. Telemetry. 6. Bistable electromagnetic relays. Mechanism. Use two electromagnetic coils to move the relay between set and reset positions. A pulse to the set coil moves the relay to one position, and a pulse to the reset coil moves it back. Applications: power distribution systems, railway signaling, alarm systems. 7. Solid-state latching relays. Mechanism: use semiconductor devices instead of mechanical parts to latch the state. These relays provide higher reliability and faster switching times. Applications: high-frequency switching, microprocessor control systems, applications requiring silent operation. Summary of differences. Type mechanism key applications: magnetic latching relays, permanent magnets, and electromagnetic fields, home automation, telecom, industrial. Mechanically latching relays, mechanical components like ratchets or cams, motor control, circuit breakers, manual override. Electrically held latching, electric current maintains position signal routing, low power devices. Polarized latching relays, permanent magnet and polarized electromagnet, high-speed switching, memory circuits. Reed latching relays, reed switches within a magnetic field, precision instrumentation, low power. Bistable electromagnetic 2, electromagnetic coils, power distribution, railway signaling, alarms. Solid-state latching relays, semiconductor devices, high-frequency switching, microprocessors, silent operation. Conclusion: each type of latching relay offers unique advantages tailored to specific applications. Understanding the differences in mechanisms and appropriate use cases helps in selecting the right relay for a given task, ensuring efficiency, reliability, and optimal performance. Creating a basic circuit example for a latching relay involves using the relay to control a load, such as a light, with set and reset buttons to change the relay state. Below is a step-by-step guide for a simple latching relay circuit using a dual-coil latching relay. Components needed: dual-coil latching relay with set and reset coils. Push-button switches, 2, one for set and one for reset. Diodes, 2, to protect against back EMF. Power supply, appropriate for the relay's voltage. Load, e.g., a light bulb or an LED with a current limiting resistor. Wires, and a breadboard or PCB for assembly.
Circuit diagramme.
Below is a textual representation of the circuit diagram. SCSS. Copy code. Power supply, plus V, plus, plus. Set button, reset button,
NO, NO.
plus, diode 1, plus. Set coil, relay, reset coil. Common contact, common contact. Load, power supply V, plus.
Circuit description.
Power supply provides the necessary voltage, e.g., 12 V DC, for the relay coils and the load. Set button, a normally open, NO, push button switch that, when pressed, sends a pulse to the set coil of the relay. Reset button, a normally open, NO, push button switch that, when pressed, sends a pulse to the reset coil of the relay. Diodes, placed in parallel with each coil, in reverse bias, to protect against back EMF generated when the coils are de-energized. Relay coils, the set coil and reset coil control the relay state. Energizing the set coil switches the relay to the on position, while energizing the reset coil switches it to the off position. Common contact, the relay's common contact switches between the normally open, NO, and normally closed, NC, contacts based on the relay state. Load, the device being controlled by the relay, such as a light bulb or LED. Steps to build the circuit. Connect the power supply. Connect the positive terminal of the power supply to one side of both push buttons. Set button to set coil. Connect the other side of the set button to the anode of diode 1. Connect the cathode of diode 1 to one end of the set coil. Connect the other end of the set coil to the negative terminal of the power supply. Reset button to reset coil. Connect the other side of the reset button to the anode of diode 2. Connect the cathode of diode 2 to one end of the reset coil. Connect the other end of the reset coil to the negative terminal of the power supply.
Relais contact.
Connect the common contact of the relay to one terminal of the load. Connect the other terminal of the load to the positive terminal of the power supply. Ensure the common contact switches between the NO contact when the set coil is energized and the NC contact when the reset coil is energized. Operation. Setting the relay. Pressing the set button energizes the set coil, causing the relay to switch to the on position, closing the circuit to the load and turning it on. The relay remains in this state even after releasing the button. Resetting the relay. Pressing the reset button energizes the reset coil, causing the relay to switch to the off position, opening the circuit to the load and turning it off. The relay remains in this state even after releasing the button. This basic latching relay circuit demonstrates how to control a load with momentary inputs, maintaining the state of the load without continuous power to the relay coils. In conclusion, latching relays offer a unique and efficient solution for various applications where stable switching states, energy efficiency, and reliability are paramount. Their ability to maintain a set state without continuous power consumption makes them ideal for a wide range of industries and scenarios, including home automation, telecommunications, industrial controls, security systems, and energy management. By understanding the different types of latching relays, including magnetic, mechanical, electrically held, polarized, reed, bistable electromagnetic, and solid-state relays, engineers and designers can select the most suitable relay type for their specific requirements, ensuring optimal performance and longevity. Additionally, a basic latching relay circuit example illustrates how these relays can be implemented in practical applications, controlling loads with momentary inputs while conserving power and maintaining the desired state. Overall, latching relays play a crucial role in modern electronic and industrial systems, offering benefits such as energy efficiency, reliability, compactness, and versatility, contributing to the advancement of technology and the optimization of various processes across different sectors.